So this is the last chapter that we'll be learning in trigonometry, and it's called Analytic Geometry, and it's all about what are called conic sections. So our first objective is just going to be to know the names of the conics. So that's all there is in 6.1. You'll see there's no homework for this. So I just want you to know the names of the conics. So the ones you hear about most often are parabolas, ellipses, and hyperbolas. But there's a couple other ones I want to make sure and mention. So when we say conics, it's really an abbreviation for conic sections that happen when you slice a cone. So they're curves that result from the intersection of a right circular cone. So the word conic is describing that they're coming from a cone and a plane. So a plane is like a piece of paper that goes infinitely in every direction, so flat surface. The lines that make the cone are called generators. So if you take two lines like this and rotate them around, the surface they create is a cone. And if you talk about a right circular cone, it means this vertex that's between the two parts of the cone is located directly above and below the centers of the circles that are at the top and the bottom. So those lines are called generators. If the plane contains the vertex of the cone, then the intersection of the plane and the cone could be a point. So if you slice just right through the vertex horizontally, the intersection will just be a point. Or you could get a line if you intersect with the cone on the surface. You could just get a line. Or you could get a pair of intersecting lines if you slice straight down through the middle of the cone. You'd get two intersecting lines. And these are usually called degenerate conics. So even if you have learned about conics before, you might not have learned very much about degenerate conics, so that might be something new for you. So I'm going to show you an interactive figure in class to get more familiar with how do you make parabolas, ellipses, and hyperbolas by slicing a cone, and I need visuals to do that, so we'll do that in class. So that's all there is in section 6.1 is learning the names of the conics. And then we move on to parabolas. So the first objective is going to be to analyze, and we'll talk about what we mean by analyze. Analyze parabolas with a vertex at the origin. So at the point 0, 0. So the first parabolas we're going to look at are going to have the vertex right at the origin. They're going to open up, down, right, and left. Those are the four possibilities. So then we're going to analyze parabolas with the vertex at the point h, k. And this is pretty common convention that everybody uses h, k for the coordinates of the vertex of the shifted parabola. And then the last thing we do is solve applied problems. Since that's always the purpose of us learning new math, is so that we can solve problems that involve this new math idea. So we're going to solve applied problems involving parabolas. Okay, so 6.2 has some skills that you really need before you start. So please make sure and review the distance formula. Make sure that's really fresh in your memory about symmetry and how you detect symmetry and different kinds of symmetry. Make sure you review the square root method and completing the square. Those are going to be super important in this chapter. And then also refresh your memory about graphing techniques, including transformations in particular. So we're going to be talking about a parabola as a geometric object. So we're departing from thinking of it as a function. So recall that the vertical line test that you use to detect whether a graph is the graph of a function would tell you that the parabola that opens up and the parabola that opens down, these are functions as well as being geometric objects, but the ones that open right, left, definitely not functions. We can tell by the vertical line test. So they are geometric objects that have equations that describe them, but they're not functions. So the definition of the parabola as a geometric object is a collection of points. So remember that a parabola is a collection of points. So when we draw them, we draw a smooth connected line, but keep reminding yourself that that's really representing a lot of individual points that are so close together that we can't tell that they're actually distinct points. But remind yourself about that. There's points on the parabola. It's made of points. So then there's a point inside of the parabola that we'll label F, and a line outside the parabola labeled capital D. Well, what this formula for the geometric object, the parabola, says is every point on this parabola, the distance to the focus, so this is the distance from focus to a point P on the parabola, and the distance to the directrix, you can see my picture is not to scale. The distance from the parabola to the directrix, those two distances are the same in a correctly made parabola. So it's the collection of all points P, so this is points on the parabola, that are the same distance from a fixed point F as they are from this line D. And the point F then is called the focus. So we use F for focus, and the line is called the directrix. This is a lot of Latin. So I'm going to show you an interactive figure that makes it more clear of how does the shape of the parabola change as the focus moves, and help you get a sense of how these parabolas are working when we're thinking of them as geometric objects. So there's a line here that we need to give a name to. That's the line. So this line right here is the line through the focus, perpendicular to the directrix, and it's called the axis of symmetry. So we could fold the parabola across that line and it would match up to itself. So the point of intersection of the parabola with its axis of symmetry, you already know this point. This is the vertex, so we'll call that capital V. So we're first going to analyze parabolas with the vertex at the origin to keep it simple while you're learning this new way of thinking about parabolas. Okay, so there's two kinds of parabolas that are geometric objects, the open up-down type and the open right-left type. So you're more familiar with the open up-down type, so I'm actually going to start with the less familiar type, the open right-left type. So they're symmetric about the x-axis. So can you see why, if you look at this equation in terms of symmetry, if you put negative y in for y, you get the same thing back? So that tells you that you have to have symmetry about the x-axis. If you replace the x with negative x and get the same thing, that's when you have the y equals x squared, and you get the symmetry about the y-axis when you replace x with the opposite of x and get the same y value. So the equation looks like y squared equals 4ax, and we write this for a specific reason. This quantity 4a is an important quantity that tells you about the shape of the parabola. So the y squared is going to be by itself on one side, then whatever's multiplying the letter that's not squared, that's going to be 4a, and it's going to be an important quantity for us for drawing the graphs. So the vertex is going to be at the origin in these first problems. The focus is located a distance of a away from the vertex. So that means the directrix must also be located a distance a away from the vertex in the other direction. So the vertex is always exactly in the middle between the directrix and the focus. So that's an important feature of a parabola. So this little table is from your book, so I wouldn't try and memorize this as 4 separate cases. I would more think about how the parabola is made, and the most important thing I think is to pay attention to which letter is squared and which one isn't. So this is basically y is squared and x is not. So that's how we know it's the type that's symmetric about the x-axis. So this one is symmetric about the x-axis. And then the other type is the more familiar one, but it's in a different looking form. X squared equals 4ay. When we think about them as functions, we separate the y all by itself. But when we're thinking of them as geometric objects, we put the squared quantity on one side by itself, and every other multiplier goes on the other side with the quantity that's not squared. So in general, the points on a parabola with the equation y squared equals 4ax that lie above and below the focus. So we have this parabola, we figured out where the focus is, we go straight up to a point on the parabola and straight down to a point on the parabola. They're each at a distance of 2a from the focus. So that's the significance of that a quantity. It tells you how wide open the parabola is, whether it's a narrow opening or a wide opening. So the line segment joining these 2 points has a fancy Latin name. It's called the latus rectum. Its length is 4a because on each side you have 2a and 2a. This is the focus and the vertex. So at the focus, the parabola is 4a wide. So that number 4a is called the focal diameter. So it's at the focus, how wide is the parabola? 4a. Okay, so that's a really important quantity. Okay, so we're going to look at some exercises, and this first one, I provided a picture so you could see it while we're working on it. So the vertex is 0, 0 with these first few problems, so that's easy. Y squared equals 8x. So this is in the form y squared equals 4ax. So 8 must be the number that equals a, and find that a equals 2. So this is the distance from directrix to vertex and from vertex to focus. Okay, so directrix to vertex has to be 2. Vertex to focus has to be 2. Then remember 4a tells us how wide is the parabola at the focus. So I start at the focus, which I know is 2 away from the vertex. Then I go up 4 and down 4, and I can draw my parabola. So the focus is at the point 2, 0. So I usually draw the pictures and then get this information off my picture. And the directrix has to be the equation of a line. So the equation of a vertical line is x equals a number. So the directrix is x equals -2. And then we draw the graph. So for the remainder of this section, the directions are just going to say analyze the equation, and it will mean find the vertex, focus, and directrix of the parabola and graph it. And so to graph it, you will need the focal diameter. So we'll do more of those together in class, and then we'll also work on these number 20 and 22 I call puzzle problems, and we'll work on those together in class. So I'm going to make another movie for the shifted parabolas so I don't go too long.